Hi, everyone. I guess we'll get started. Welcome to the holiday episode of the Haskell Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. And, what better way to spend the eve before Christmas Eve than to learn about monoids and semigroups? Today, we'll be covering uh, or begin our exploration of the various type classes that are built in Haskell, particularly in this realm of what I started calling type algebra design. Although some folks are like, Is it really a type algebra? You're doing algebraic data types." Uh, but as we go through today and these other type classes for the next couple of weeks, which will include monoids, semigroups, functors, applicatives, and monads. Um, it will become apparent that this is really an algebra in the mathematical sense, and we will be discussing that particular comment as we go through our discussion today. A couple announcements for our viewers and those who are in the Atlanta Functional Programming Meetup page. We are retiring our Google Hangouts link. We have now permanently moved over to Jitsi for our streams and our live discussions. So, for those of you who are on YouTube Live and would like to participate in the live discussion, please feel free to join our meetup and you can grab the URL to the Jitsi link there. Um, Obviously, we would be more than happy to accommodate and get questions. I'd like the online community's questions coming in from the YouTube live after the streams. So by all means, if you are watching this after we have streamed and you have questions and discussion points, feel free to make comments in the YouTube comment section, and we will either answer your particular question directly on the YouTube video, or if it's something that requires a much larger discussion, we will bring up in the next live stream of the Haskell study group. Our agenda today is a little bit in a little bit of a different order than what was presented. If those of you who are following along in the Haskell book, chapter 15, which covers monoids and semigroups, particularly because of the fact that although they do present both fairly regularly, the one thing that I found confusing when we looked at the signature of the monoid is the fact that we needed to kind of know what a semigroup is a little bit, and later on, some of those details kind of be gets cleared up when you actually look at what a semigroup is. But because they claim that it isn't really necessary to know what a semigroup is to understand what a monoid is. Looking at the signature of the monoid might look a little jarring. So I thought it would be just best to present both monoids and semigroups, their type signatures first, and then we'll start discussing what is a monoid and what is a semigroup and so forth. Both of these are actually available if you simply go in. Sorry, I'm going to my REPL here and import data.monoid. Remember, yeah, and we do a info on monoid, and you can see that um, the monoid actually is defined as such. And as I mentioned before, um, monoids kind of require that the type that is being passed into the monoid is also a semigroup type, and we'll get into that in just a minute. But I'm just going to go ahead and copy both of these into our REPL for later discussion. Sorry, our buffer here. And it's just important to kind of keep these in mind when you are looking at uh, the type classes themselves and their signatures and what they represent. So this is what the monoid is defined as, and this is what a semigroup is defined as essentially. Okay. And the semigroup itself is of a different uh, it has only one particularly important implementation that you need to provide for your type, and then it'll become a semigroup. Um, to begin with, though, to discuss what these two types are,
Hey,
we
Rob,
must.
I just had a connection issue. I'm not sure if you guys.
I don't believe I'm having a connection issue as of yet, but uh, that's
I
just
can
me.
hear. I could hear the presenter, Ram, but I couldn't hear maybe Judd very well when you were trying to find out about connections.
Okay. Yeah, Judd, you may need to. You may have some connection problems on your end. I don't believe that is uh, that is an issue for me at least.
Okay, it's my side.
Okay.
Okay, cool. Let's
All
go
right.
forward. Sorry about that.
No problem. Um, Before we start going and dissecting these two different type class interfaces here, and kind of figuring out what their differences is, we must first understand what I mentioned earlier, which is this approach to designing um, types inside of Haskell and designing particularly um, types that can be integrated well in Haskell. This approach is actually characteristic of application development and program development in Haskell, and requires essentially defining what an algebra for a family of types. Okay, so what do I mean by an algebra? I think this is a first thing. Like for most people uh, who are thinking of algebra, they may be thinking of simple things like the what we learned in school with equations and unknowns and so forth, quadratic equations and Cartesian and learning about the Cartesian coordinate system, some advanced topics on graphing. These kinds of things are typically what most people think about, and it's usually from high school algebra. But really, algebra stems from this field of mathematics that essentially uh, talks about a set of objects, or it doesn't have they're mathematical objects, okay, and the operate, and more importantly, the operations upon which the set can operate over. All right, meaning that the set is closed under these operations. And it's an advanced topic. Modern algebra goes through many different things. And a lot of category theory and stuff is a generalization of some of the stuff that's available in modern algebra and modern abstract algebra. It goes above and beyond what modern algebra provides, and actually abstracts it even further. But at the heart of it is operations and sets of mathematical objects. Okay, this is probably the simplest way of thinking about it, without getting into too much of the nitty gritties of math, of pure math, and actually going about it. And what you want to know about an algebra is that when you're talking about designing the algebra, you're not necessarily worried about the values that are members of the particular set upon which you are operating over. You're just trying to require that if it is a member of this set, regardless of its value, it must adhere to these operations that are defined for this particular set. Okay. I know I'm speaking in very abstract terms here, but unfortunately, until we get into some examples, the only way to talk about algebras in general is through abstraction. So my apologies ahead of time. I know it may sound a little confusing, but getting some of the terminologies available is important. Okay. Um, the reason why we talk about algebras within the context of Haskell is because, and I've mentioned this when we talked about this topic before in previous weeks, as I understood the concept of type classes, but essentially type classes are defining, when you think of a type class, you are defining the set of operations upon which a family of different types can define, okay, and be closed on. So in order for them to be our the in order for a particular operation to be available for a particular type, if the operation defined is in the type class, you have to define an instance of that type class for that type and then specify how those particular operations should be defined. All right. And this is what we are defining as algebraic type design. Okay. At least this is how I understood algebraic type design. Basically, you're separating the operations from the actual type itself. Okay, and when the type defines an instance of the type class and the operations, then it's closed under that type class and it becomes an instance of that type class. All right. This is important because it ends up being used as a requirement. It can be used as a requirement actually when you're defining functions that require certain characteristics to be available on a set of one or more types that may be disjoint. They may not have inheritance hierarchies or anything associated with that. Um, they may be completely represented in a very different way in on a computer, but they all have one or more operations that share the same kind of behavioral characteristics, and you have to just define them accordingly. One example of this is all the different numeric types in the numeric type class that we've seen before. Okay, so within this context, we have two fundamental types upon which everything type classes upon which everything else kind of builds on. Right. This is kind of what is important to recognize. Um, the first one to understand is really monoid before we talk about semigroups. But semigroups is necessary because, as you can see, semigroups is kind of an important. It's actually a constraint upon which is, if your type isn't defined and doesn't define it, monoid doesn't necessarily uh, won't necessarily allow you to create an instance of itself because you didn't define this particular operation. Now, for those who are just joining us and require a quick recap of what type classes are kind of like interfaces for classes of types. All right. And so, in order for you to really, one second here. In order for you to actually go and define a particular instance of a type class, you need to define all the operations that are required for that type class, plus any operations that are required, any type constraints that are required for that type class to be adhered to. So you need to, in order for you to define a monoid instance here, in this case, you have to define these three functions, which I'll explain what each of these functions mean in a minute. But in addition to that, you also have to define the functions that are all defined in semigroup too as well, which means you have to define an instance of a semigroup. All right. So putting that all aside, um, let's talk about monoids in general for a very and give a very precise definition of what that is. Okay, a monoid is nothing more than a um, a binary operation. This is how the book defines it. I don't entirely sure uh, if I agree with this definition, but it defines it as essentially a binary associative operation with an identity. All right. I would say that this doesn't completely cover what a monoid is, but it does give you the characteristics of in order for something to be a monoid or having a monoidal operation or being closed monoidally. All right. Depending upon how you use the term. Okay. So you have a type. All right. Let's say a type A. Okay. Actually, before I get into to defining a monoid, let me first break this down here, right? So we all know from arithmetic um, what the associative property is for addition, okay, and even multiplication. But you can actually generalize that concept of associativity to any operation. So if star is some operation, all right, then associative associativity can be defined as the order in which you actually apply the operation to arguments does not matter. All right, so you can parenthesize the A and B in this case for A, B, and C being instances of a particular type, being instances of a particular type. You can apply the operation to A and B first and apply then C the operation on C and the result of A and B, and it'll be the same as if you applied the function star on A and the result of applying the function to B and C. It will be the same thing. That's what associativity is. You could group together particular things, and the order in which you group them will not affect the particular result of the. So that's what a a associative binary operation is, all right? But what is identity? Identity comes a lot from mathematics, and it's actually a member in many things when you talk about modern algebra. But the idea of its identity is for a given operation, all right? For a given operation, for a given operation, star again we'll use, all right? Um, there is some value, okay, or you could say there is some value, okay, for this type, in a type A, such that for any other x in A, okay, for actually it's for any x in A, okay, and let's call our value I, okay, x times I equals x, all right? That's all that means. Basically, if you apply the function to both this value I and x, you get the x back. You'll get the other value back, not the identity back or some result, a different value, all right? Now, what I'm showing you here is specifically what's known as right identity. We're basically applying a function to um, uh, to I on the right hand side of the value x. Okay, there is two different types of identity. You have left identity and right identity. It's really the order in which you are using the identity value with the operator in an expression. Okay, so left identity is usually defined as I times X for some value I and operation star. All right. And right identity is what I just showed you earlier, which is defined as, one second, uh, some reason I lost that left. Identity is I times X. Right identity is this guy. All right. Now, both of these are still going to be the same thing. All right. So your I times X and X times I are both equal the same. You'll always end up getting X back. All right. For any of these. This identity piece is particularly important because later on when we start using monoids for different operations, particularly when we start talking about reductions or catamorphisms, as Haskellers all seem to be all in the they use catamorphism as a phrase as the phrase for folding or reduction operations. Um, this will become important because it's actually leveraged quite a bit, especially when you're dealing with like large data sets or values where there's maybe an odd number of values, because then you could just throw in the identity of that given operation, that given monoid, and it will actually go ahead and work its way up. Okay, so there's a question. It is interesting that associativity is part of the definition, but not commutativity. If you had the latter, then there wouldn't be. Okay, so this is a very important point. A good question and interesting. So yes, associativity is part of dealing with when you're dealing with monoids. Associativity is a big part of the definition, but you can also deal with if you have commutative operations. There is a commutative monoid called I think it's called the Abelian monoid, which is named after um, kind of like the mathematical uh, uh, the modern algebra Abelian group concept. And I think that actually implies commutativity that allow you to have commutative operations, but you don't need an operation to be commutative to being monoidal. And there are cases where something is monoidal, but it's not commutative. An example of this is matrix multiplication. All right, matrices are have identity. All right, they have a left identity, a right identity. It doesn't matter which way you apply it; it'll be the same. Right. Um, But if you try to multiply two matrices in the wrong order and one of them isn't and both are not the identity matrix, you're going to get a completely different, you could get completely different results. All right. Um, obviously the case of this is uh, um, in fact, I would argue that you may not even get results when you try to do commutativity, because the only time commutativity would ever work in the case of matrix multiplication is if you're dealing with square matrices. All right, square matrices are where you have two m by n matrices where they all line up. So there, if you have two 4 by 4 matrices of different values, then yes, you could probably make them commutative. But if you're doing like general matrix multiplication, associativity can work because things line up in that particular way. So your columns of the left matrix is always going to be aligned with the rows of the right matrix, and so on. This is important to note, right? So, and if you group them in a particular way, they will still line up regardless. So the associativity aspect is very useful. Other questions? Um, but the point about commutativity, it's a very interesting thing. There is an abelian, if I remember, I think abelian is a very available. but I don't know if it's available without me doing maybe data.abelian. Interesting. Always have to go to Google for some of these Haskell things. Search for abelian. There it is. It's interesting. It says that abelian is defined. Oh, it's defined in import. Let me see if I import algebra. Do that. Algebra. Is it data.algebra? Maybe. Let me see. Data.algebra. Oh. So this is interesting. It's defined in abelian is defined in Hugel, but it can't seem to be. It's not being found in when I run this, which is really odd. Okay. Folks who might have a different. I may have an earlier version of Haskell here that it may not be defined in, but I'm pretty sure it should be defined. But I'll move forward. If you just look up abelian in the in Hugel, which is the Haskell wikis based search engine that allow you to look up type classes that are available at your disposal. It is there. It is defined there. I just for some reason can't seem to pinpoint what is causing the load not working the way it should. The import, sorry, the import. It may not be available in Prelude. I may have to define something else in order to get the abelian type class. Okay. So we talked about associativity and we talked about identity. What is the big deal about this? What exactly is do we need to do in order for us to actually go and define um, this associative operation inside uh, for a monoid type class instance if we're defining one ourselves? Okay. Um, well, let's go through the names and how given that we know what a monoid is, let's go ahead and break down this type class definition here, just so that we know what operations we need to define as. All right. So when we talk about monoids, okay, in Haskell, we have three particular operations, okay, and each of them is actually associated with the definition, okay. Um, The first is the identity operation. And in the monoid definition, that is defined as MMT. Okay. MMT is essentially such that when you're defining your monoid instance, MMT is guaranteed that if you define MMTA or AMMT, which is both defining the left identity and right identity version of this. And again, I will write some executable code for this, but we'll go through the instance of say integers to kind of like break it down a little bit. But in a sense, this MMT thing is defined as so that if we have some operation MMT. Get this kind of like interesting. Yeah. So if we call mappend, which is our associative operation on MMT of some value x, it's going to be the same as if we called mappend on x and MMT, which is going to just give us x. All right. We'll see an example of this when we start going through the identity operations in uh, particular types, and this should become very obvious to you then. One of them is obviously the numeric types, and then we can go through it from there. Another thing that I want to mention is Append, like I said earlier. This is when we talk about this is left identity equals X, and then obviously our right identity is this Append X MMT, and in both of the cases, this will be X. So if we do this, we have X in both cases. Append, like I said, is the associative operation. You can define it any way you want to in terms of uh, of your type. So your type is really going to determine how you want to define associativity for that given type. Um, there's also this mconcat, which I'm guessing is based on the type definition here, is essentially going to do a reduction on an mappend. So it's going to take essentially each value in the list that you're providing and then do a reduction on it by calling uh, uh, the appropriate associative operation on each value and folding it essentially into a single value. All right. Um, so this is why you have mconcat and you have mappend. Uh, if you actually look at the type definition for the monoid here, it doesn't actually provide an implementation here, but the book actually says that, and it's particularly interesting. I'm wondering if they actually changed this. Um, the original implementation actually included the following default definition, which is mconcat is equal to a right fold or fold R of mappend on and MMMT. So again, folks who are reading this is a partially applied function that's taking in um, our function that we're going to create. It has the first argument, and it's getting our initial value, which is the identity, has our second argument. And if you remember, fold R actually, and we could just show it here. It actually takes in a function, an initial value, and then it'll return you a function that'll take in a type A, and then that's foldable, and then it'll create a B. Okay, so here now your mconcat will automatically, work on any type that, as long as it adheres to the monoid type, because it needs to have MMT defined for it, and it will work for any type that has those two definitions available to you. Okay. Notice this is a different way for folks who are looking at this and says this is just a generic algorithm. That's how I've kind of viewed this. Like, and I'm still trying to see what the difference is between doing this approach to type design than saying like something like say in C++ where you define operations. Um, uh, and create generic algorithms on top of that. Now that we have C++ concepts, you could look at this type class definition and see the similarities between defining your operations for the concepts and then creating generic algorithms that, as long as a type adheres to those concepts, you can actually go ahead and instantiate the template and generate a new version of that type. So there's some very close similarities, and it's not surprising because uh, concepts and generic programming have been around for a long time, and I'm sure the languages kind of over time kind of influenced each other. So it's, some of these bits and pieces are definitely connected. Um, so I've kind of focused quite a bit on monoids, but I didn't actually talk about what semigroups. But I mentioned earlier that semigroups is important because, as you could see here, um, semigroups need to have this a type needs to be a semigroup in order for the monoid instance to be valid. Okay, has that definition. Line 26 shows you a semigroup is nothing more than the binary associative operation without the identity. So you do not need to provide the identity to be a semigroup. But if you have an identity, you are a semigroup and a monoid. All right. So if your type has an associative operation, so you can actually associate with it, then you have a semigroup. All right. But if it does, if it doesn't have a an identity operation, which means if you can take any value as a member of your type, and there doesn't exist a value that if you apply, say, the associative operation to any given value of that type x, that you can't get x back, you don't have an identity. If that doesn't exist, then you by definition do not have a monoid. Okay. And again, an example of this that I can think of right now is uh, general matrix multiplication. Well, actually, general matrix multiplication is monoidal because you can actually go define that with identity. And we think of something else. It is uh, a good example of something that is a semigroup but not a monoid. That is I can't think of a good one right now that's mathematical. That's it's usually very difficult when you're defining it, but basically it boils down to if you can't figure out this unique identity for the given type, then it by definition is not a semigroup. Well, sorry, it's by definition is not a monoid, but it could be a semigroup if you can associate. And association means typically if you are applying the operation to. Good point. There's a good example here. So one of our attendees gave a great example. Yes, if you try to use natural numbers with so natural numbers for folks who has a quick review, if you use natural numbers, so natural numbers are your counting numbers. So we're starting 1, 2, 3, and so forth. Um, those are definitely a semigroup under addition, but since there's no 0 in the natural numbers, um, by that definition, it cannot be a monoid because under addition, the identity for the positive integers, sorry, the non-negative integers is 0. Actually, that's right. So we don't even have to say natural numbers. Really, it's positive integers. Natural numbers, I'm always afraid of saying natural numbers do not include 0 because I've seen definitions where some say it is 0 and some say it isn't. It doesn't include 0. So I can never be sure about natural numbers. But if we say positive integers, then we know the set of integers x where x is greater than 0. In this particular case, this is a semigroup under addition, but is not monoidal. Okay. So this is very important to understand. When you say it's something is monoidal, it has to have um, a this identity operation, and if we define the set correctly, it becomes important to recognize that it could be set it it may not include the necessary identity operation for it to actually be closed under that and become a monoid. So let's look at a couple of examples. Um, of monoids in action. Okay, and I kind of alluded to this already. Um, that monoids have a lot of different different definitions. Okay, um, but the most logical one to kind of go through and kind of understand is probably probably lists. Okay, because this is probably the best way of actually figuring out stuff. All right, so lists are monoids because under uh, specifically concatenation. Okay, there are other. I think there might be another place where they're monoids under, but and we'll touch base on that because that's very important when we talk about numeric types. But we're gonna just focus monoids under concatenation. What do I mean by this? Well, um, what is the identity of a list? All right, when you are again, in order the identity is you apply something and get the list, you get the other. Um, if we apply a list, something to this list, we get the original list back. Well, in this case, obviously, if you guys have already guessed it, it's going to be the empty list. Okay, and the associative operation we're going to be talking about is concatenation, which in Haskell is the plus plus sign. So let's look at a couple of examples of working with this here. If we start out, let's show that we have left and right identity here. Um, so we could just simply do m append on an empty list here. Let's do 5. Okay, and we see that we get this. We know that we have right identity because we can apply this to the empty list too as well, and we get the original list back. We also can apply this to non-empty lists, and we'll get um, the concatenation of these two lists. Okay, when we call them, we can also do what I said before. Like if you instead of because M append, the important thing to recognize about M append is not just associative; it's a binary associative operation. Okay, which means it takes only 2 arguments, okay? So obviously, if you want to deal with multiple arguments, you want to have some sort of reduction function, and this is where mconcat comes in. You can actually provide a list to mconcat, and you are essentially doing what you would have done if you defined your own reduction function to go under and concatenate every sublist that's inside this list of lists, all right? Which is pretty cool. Um, this kind of shows you that concatenation is a very useful uh, thing to have, right? And in fact, if you actually look at, I don't know if I can actually grab this and show you directly in the REPL. I wish I knew more advanced features on how the REPL works, but essentially, a lot of definitions for lists actually uh, for their semigroups, and they actually define the associative operation as being, and again, this is the shorthand, the infix operator for associativity, to being plus plus. Okay, and this is just so that they made an infix here without having too much trouble. And then obviously they could just then define instance of monoid of A where empty is identity. Now, you may be wondering why I defined our in our why this is defined in Haskell as being just empty and doesn't have append or mconcat defined. It goes back to this meta syntax here that we've seen before. This is in order to implement the monoid, you need to have the bare implementation of the monoid, which is really defining the identity element. And if you did that, since a monoid requires a monoid instance requires a type it's creating an instance of be also a semigroup, it will take the semigroups implementation for the associative operation and use that to define mappend and mconcat directly for you. So all those other functions will get generated. All you need to define is the bare minimum functions, and then everything else that just calls out to those functions will get generated appropriately. Okay. So we've kind of talked about, um, you know, monoids for lists, and we've actually looked at the different monoids here in in our implementation of in our REPL when we looked at the what available instances are available for a monoid. I would recognize the fact that for our numeric types, which obviously have monoidal operations, um, it can be seen that integers in all the different integer types do not have actually a monoid instance defined on them. And you may be wondering why that is. The reason is from a mathematical perspective, technically, there are two different operations that are monoidal for the integers. All right. Summation is monoidal, which means you could actually add numbers together in a monoidal fashion, okay? Because remember, identity is 0 when you are adding numbers together, and then you can, you can associate them in any way you want to, and you'll still get the same result. But in addition to that, multiplication or product is also a monoidal operation for um, integers, because identity in that case under multiplication, identity is 1, and then you could still do the associativity for um, has defined as I showed earlier, for integers, you'll get the same result. So what is the big deal about this? Well, Haskell has a rule when it comes to defining instances of type classes, and that is for any given type, you need to actually have only one unique type class instance. Well, in this case, technically we should have two instances for one determining products and one determining sums. And that's exactly what Haskell did to kind of work around this. They said, well, because we are saying as part of our design, this steadfast rule that for any given type, we can only have one unique instance of the type class in order for it to be of that type class. Um, we need to somehow, for sums and products, we need to go and define special types to essentially define those two things. And they are, as you can see here on the screen, the sum type and the product type that's here that's going to be specialized on integer. Okay. And we'll see an example of this because this was a particularly interesting thing that the book kind of mentioned that I was like, huh, that's an interesting point. I didn't realize that they can actually do this kind of like that's a good workaround actually to work out and still keep the type system clean by just simply defining these two additional types. But they are really wrappers for folks who are looking at them. They are wrappers. They're wrapping around integers, numeric types in order for you to do this. Okay. Um, so to kind of give you an idea on what this kind of looks like, if we go ahead and use, sum 1 and sum 2 here, you could see that we'll actually get a new sum that applies the associative operation on the two values there, sum 1 and 2, and you'll get the same, and you'll get this get sum 3. And you'll see this is the same as if you did sum 1 plus sum 2 here. Well, and you'll get the same sum. When you see sum and then the concat operation, when you're concatenating, because really I'm saying sum 1 plus sum 2, but really because I know the associative operation that we're dealing with is addition, but really is you're associating sum 1 with sum 2, which means you'll get this reduction, which is sum 3. The same thing is if we use products here. I'm just going to start using the shorthand here. Product 2 and product 5, you'll see that you'll get this get product. Now these are new types. They are actually new types that are defined on summation and multiplication. All right. So uh, one second here. I'm just looking at my notes here regarding about. Oh, right. So the book kind of mentioned a particular topic here that I just want to briefly mention, just so for folks wondering why I'm not going to really cover this, but there's a reason for it. But basically, the book kind of gave kind of a quick overview on why these are new types and why are we using new types in general. Basically, new types, if you remember, new types are basically if you define they're a way of defining type constructors. So you could define, say, some data constructor foo as in foo string, but this is the same as if you actually defined a type called foo prime, and this is equal to foo prime of string. And this is essentially the same um, type. Both of these are technically the same type, same representation. There isn't much semantic difference between these two, but the one thing that new type does in Haskell is that it constrains the data type to only having, if you recall, a single unary data constructor, right? Meaning that it can only, unlike data, which could have fun type, I'm sorry, could be a sum type, so it could be foo string or foo bool, and it will, still be the same, sorry, bar bool, and it could be the same here. Um, this cannot actually have a new type cannot actually have multiple constructed types. Sorry, it could not be consisted of multiple type constructors. Right, it can only have a unary data constructor, and that unary data constructor can only take one type. And this is really associated with the secondary requirement of new types, and that is the runtime representation of the type when it gets compiled and what it wraps should be identical. So that means the new type that you're defining here is nothing more than a semantic piece of code that's you're using behind the scenes for getting type correct code when you're developing your applications. But at the machine level, they are the same representation in terms of the data storage. Okay, for folks coming from the sea world, and I think this is a good analogy that the book pointed out has is think of a sea union, a union data structure with one specific single member, um, and it avoids creating what's it it avoids creating an extra pointer so that you don't have but at the same time you don't need to worry about it mixing up many different things like a normal union that share a single representation, okay, because of the fact that it requires only that type to be available and nothing else, okay. So when you're talking about union data structures, most people know this data storage wise in C. It The data storage is going to be the size of the largest member of the structure. And Haskell kind of prevents this by saying, well, we can only have one type, and we are going to enforce the runtime overhead to being 0. It's going to be the same runtime overhead as the underlying type upon which it's quote unquote wrapping at the high level. Um, New types are particularly important as you start writing larger programs when you are trying to signal intent. And like I said, it improves type safety, particularly in cases where you are dealing with, and I think of the same thing as type for type aliases too inside Haskell. it's particularly useful when you have different, technically different types from a semantic point of view, representing the same underlying type, right? Like in whether it be an integer, string, or what have you. But by having the semantic difference, the type checker can verify if you're passing in one thing of one type into another thing of another type, even though they're represented the same way. An example of this is if you have a type, if you're doing angles, this is typically an example that I kind of come up with when we're talking about um, where type aliases and I think new types can actually fit in. If you're talking about angles in geometry and you want to represent angles in degrees versus angles in radians, the underlying representation of the actual angle in memory could be a double, but you don't want to pass in something that expects degrees, something that is in radians, because your calculations will all get messed up. So so even though they're both technically doubles and the operation can succeed, you have to be very careful. So you'd want the type checker to recognize, hey man, you're using the wrong units, right? So this is one way of actually working around that. Sums and products are types are not actually restricted to um, well, they're restricted to all numeric types. They're not restricted to just integers. Okay, we can actually see this if we attempt to actually use sum to actually concatenate, say, hello and world. All right, it's going to go and complain that you can't actually take a numeric instance of a string of characters. Right. Which is correct because we didn't. There's no such thing as that. It's the same thing if we try to do. If we just simply do sum with product here, and we try to actually run this, you'll see that it's the same problem. All right. Um, and again, it goes back to what we were talking about before. It is. Oh, sorry. You'll see that you get the same instance direction there, right? Obviously, you can't mix sums and products. That's why it was complaining earlier. The one thing that might be a bit jarring for folks is the fact that since you are using a higher type and you're wrapping this value, you need to actually grab the underlying value from the result of the operation. Okay, this is quite logical, but as you can see here, we have a field accessor. All right, we do have a field accessor, and that's actually specified in the what the show. The show is actually telling you what field accessor you need to use. So if we ended up using, say, let's try product 2 with product 5 again, okay, and we want to actually get that product, we can actually do get product and then just grab product 2 with product 5, and you'll see that you can actually get the value from that, which is very useful. The same thing is actually with get sum. Get sum, um, it can be used the same way. We can actually go and grab, say, sum 1 plus sum 2, and we can get the actual value from it. I thought was pretty neat too. So don't worry about those other questions, not being able to grab those things. They are available through field accessors. Again, for folks who are just joining us and are not used to the dollar sign, remember the dollar sign is nothing more than um, removing a set of parentheses. So in this case, it's removing the set of parentheses associated with me using wrapping essentially sum 1 you can fix with sum 2. So this is the same thing. I'm just going to pause a minute for questions and just take a quick sip of water. Okay. So why are we actually talking about, um, and I think this is a particularly important thing to recognize, just laws related to properties associated with set of types and the operations that we're closing on them. Well, Haskell's one of the design principles or driving, I would say, driving motives around designing stuff in Haskell or implementing stuff in Haskell or even developing stuff in Haskell is the notion that programs are proofs, and if you've composed a program correctly that is type correct, it should be it should prove its correctness, minus the fact that it may not implement the runtime behavior as expected of a particular user. It is fundamentally correct with what it's defined has it what it's defined as. All right, so whatever it is actually defined. Um, I think it's important to recognize this because when we are talking about building up these types, it becomes very useful to know what um, laws you are trying to essentially respect. Since these type classes are essentially defining operations upon which you are adhered to, knowing what ultimately at a conceptual level that type class represents will allow you to know what laws you need to make sure your implementations respect in order for it to be properly correct and it can compose well. Because one thing, again, is since we are dealing with a pure functional programming language and we are dealing with types, when types line up and they're type correct, you can actually compose different pieces of the functions that are taking one type to another to make higher order functions, and you can actually build them towards the sky. The sky's the limit in terms of what is capable and what it's not capable of. So that's something that's very important to recognize when you are actually going through this approach and trying to understand um, uh, these uh, these different type classes. Okay, whether it be monoids or semigroups, because monoids and semigroups, again, like I said, they're actually pretty simple. Semigroups are nothing more than groups with an associative operations. Monoids are essentially groups that have an associated operation and identity. But the fact that they need identity and that they're associative are the properties upon which you are proving essentially that the type is closed under, and you can actually um, uh, leverage it as is, knowing fully well that the properties of the underlying type is preserved. So very quickly, I'm just going to just wrap up here. Um, we talked about integers having multiple monoid representations, but we never actually recognized that there are probably other types that could have multiple um, representations that are closed under monoids. Okay, and but the design that is required when you are dealing with essentially multiple monoidal operations for a given data type is to essentially create new types to distinguish them. And what I mean by new types is using new type keyword and create a single unary data structure so that the underlying representation is intact for both the new type and the type upon which you are actually trying to define the new monoidal operation on for. All right. Um, when we talk about, for example, the simple example for monoids and defining monoid types, you need to think about the associative operation has an append, and appending is classical, is typically classical, um, uh, regardless of type, because we've seen it in other languages where addition is used as the operator to determine whether you're appending, two different types, whether it be two different strings, or if you're doing uh, although in the case of like vectors, obviously you can't use the append operator just because of the fact that addition, usually people would like to use the addition operator for actually meaning addition between two vectors. But you might have a different operation there that's just representing appending. List concatenation obviously has a plus plus operator in Haskell, but there's also, you can also define mappend to actually define this. Okay. Um, Many different types of operations essentially defined has this associative append operation, but you need to think about what exactly that means when you're combining two values with respect to this particular operation, and then use that to actually define your mappend function for your given type. Okay. And the reason for this is when you're talking about combining values using mappend and monoidal operations, you're essentially talking about, again, goes back to what we were talking about earlier, folding, essentially. All right, folding different types together. Okay. And so the one thing is, when you're looking at it, is to recognize when you are going to be defining um, this is how are you folding values has to become essentially a key topic of the conversation when you are talking about because reductions, when you're almost always talking about reductions, and you're talking about, and I'm using reductions because there are folks coming in from other languages that have reduce. All right, Lisp has reduce, Common Lisp has reduce, other functions have reduce. I think C++ has a reduce operation, Python has a reduce, and so forth. When you're talking about reductions, um, uh, obviously, um, the notion of combining these two values and their associativity comes to the forefront, and that's when especially if you're talking about a reduction of a type that has an identity, um, that you're dealing with essentially a monoidal operation. You can actually work your way through actually defining generic operations, assuming that that's there. A lot of things end up becoming essentially generalizable to being some form of fold. Um, One example of um, uh, another monoid, wait, another type that has multiple monoids is actually um, Booleans. We know that Boolean, if we recall, if we do an I on bool, I think, yeah, you'll see that the data constructor is either false or true. You could define a monoid um, on conjunction, which is and define a monoid on disjunction, which is or. All right. Um, in in data.monoid, actually, they do have something called all. Sorry, I all, and this is essentially a new type on Booleans, essentially, that will allow you to define a binary associative operation and make it a semigroup, and then identity, of course, for one or the other depends on what you are talking about. In the case of um, and uh, if we do MMT on, I think, true, it's uh, all true. Get the MMT on all false. Going to be the empty set. So if we do append on all true empty, what do we get? We get all true. So if we have the empty list, if we don't have any horn clauses or any Booleans that we're dealing with, then we have the empty list. And it's the same in the case of disjunctions too as well. So we can leverage this actually to start out with the same value, and it'll give us the same thing. Like if we apply append on an empty of all true here too as well, you see that it has a left identity, right identity. So let's see this all. All is used for conjunctions, and I think any is used for disjunctions, right? Yeah, any is used for disjunctions. Okay, so we can see this obviously if we do all, yeah, all true. You don't need to actually wrap these, but I'll certainly do so. All true, and you'll see that you'll get all true. But if you do all true and you try to apply all false, you'll get all false, because obviously all true and all true and false is false, obviously, right? So this is very useful. We can actually see that again, if we do all true. If you're using mappend, I encourage you to actually specify all true and all false, and you'll get the same answer here. And obviously, since we're dealing with this here, we need to call get all if we're trying to use all true, all false, and let's see what happens. Oops, sorry. That's what happens when you don't use dollar. Also do this, which is a little which is just a what? Oh, interesting. It would not allow me to do that. So I do have to specify. Okay. Oh, this. You can see that we're getting that too. And if we do any, obviously any true and any true obviously will work. But if we do any false and any true, you'll also get true, and we'll keep going through. The only time this is ever going to be false is if we do both or all, everything is false. And you can just to show this, we could get any. You can do any false and any true, and you'll get true. Finally, to show you guys that you can actually work this out here, we do all true, all false, all true. You'll see that this is going to give us all false, and the opposite is going to happen if we provide any false. Mconcat can work on anything that has a monoidal operation. So what we saw earlier with sums and stuff, you can actually also do that too as well. It will be a very useful thing to recognize. Another example is the maybe type, which I was surprised at. I'm still trying to wrap my head around. So we're just going to go through the example here. So basically, they have this operation called first and this operation called last. All right. So if you, since there are two possible monoids dealing with essentially either dealing with the leftmost argument or the rightmost argument in the maybe type. Okay. So if we look at first, we can actually see this. I think it's if I do, yeah. First is this new type that'll take a maybe, and it'll get the first value, which is the leftmost value in the monoid, and then work its way up. So in order for us to do this, we have to first, sorry to use first so many times, but we have to, we need to, as a prerequisite, we need to provide some constructions of a maybe type into first, and then work our way through then an example. So let's say that we have two values, x and y, okay, and we try to essentially call mappend on x and y. You'll see that we'll get the leftmost argument, all right? If that's the same if we do this too as well, okay? If we actually change this and made last instead, okay, I'm just providing two other values that have the same values here, and we call then x prime, y prime, you'll see that it'll get the rightmost argument, okay? Sounds very simple. You have a pair of stuff. In first, you're getting the first. In last, you're getting the last, all right? But because you have this, a maybe type, because maybe is either just or nothing, okay, remember, maybe is just taking the wrapper of the type or nothing. Nothing is going to be our, um, we'd have to do first nothing or x, and you'll see that you'll actually get the right most argument in this case. Or if we pass in first nothing here, you'll see that we'll also get the leftmost. So we have left identity, right identity. And this works regardless of if we do, because nothing is the identity for is a part of maybe, right? So if we do last and we do the same thing, okay, we'll get the same thing here. Okay, last x prime, last nothing. All right. Um, just don't try to, mix things, because then you'll get this error. All right. Um, one interesting thing to note for folks who are wondering what this is the same as if you did this. You'll get the same thing. And get last, remember, is just a field accessor that you can just call on the result. So when we look at monoids or monads and what's been defined in the actual signatures, you may notice that every type that's been defined is taking in a monoid, and it's returning a monoid. Okay, this is particularly important because um, the monoid's obligation is to uh, provide an encapsulated type, even when all possible values of the larger type may not be able to contain the value of the given type argument. All right, like that's a very important piece. That I'm quoting directly from the book that I wanted to understand. This particular piece is very important to recognize because This actually has a direct effect on, say, how you are um, defining your own types. Okay. Um, the encapsulated typing existing when not all possible values of the larger type contains the value of the type argument means that the underlying type, let's take in the case of maybe, all right, um, it's asking that it everything kind of exists, all right. Um, and the reason for this, an example of this actually, which will drive this home, is what we were just using with maybe. Okay, um, maybe has nothing in jest, like I said. Um, maybe does not actually contain anything that you would use for monoids. All right, but jest does because it has a non-zero value. All right. So because nothing in the type signature, I'll show you this again. Look at maybe again. Go back to maybe. Because nothing itself is a nullary type constructor. All right. And but just is a unary type constructor. Um, you can't actually have either or being like returned by the monoid, and especially the monoid in this case is it doesn't know that it will contain what something that you're trying to get a monoid for, like in maybe's case, because nothing, there isn't anything there, all right, that you're unwrapping, all right. So what this means then is when you are defining your associative operation, all right, you're going to have a case to deal with this nullary construction, and you need to actually then build and account for um, this possibility that there might not be a type argument in your type constructor, all right, because it's a nullary type constructor. Um, and because you don't have because you have a nullary argument, type constructor, sorry, um, the type checker treats this very specifically, all right? Um, what it does is it will actually, in the case of monoidal operations, it will not demand that the nullary construction have a monoid instance for that given type. It'll just, assume something else. All right. Because and that's pretty weird, if you're thinking about it, um, from the standpoint of generalizing in the case of normal functions, that this is a special case. But again, um, we have to recognize that for certain types that could be monoidal, their base type, their nullary type, might be the identity type, and we may not be actually ever going to grab that type information by unwrapping the type. We may just need to just say by default, if there's nothing there, go ahead and return accordingly. All right. An example of this, just to drive this home, is let's say that we are using Booleans. All right, let's make our own Boolean. This is a very interesting one that was in the book. All right, so let's say that we created our own Boolean. This is in from page 589 in the book. Okay, chapter 15. Which again, folks following along, I encourage you to take a look at this and try to understand what it's doing in the book, and even try it yourselves. And grab, you know, you have the sum type, all right? And let's say that, so that we can actually display it. Um, we could define a semigroup on this using for conjunction specifically. Okay, that's and for folks who the logical and. Okay. Um, And we could define a monoid on conjunction for this Boolean type by first defining our semigroup, all right, on the Boolean type. And this is defining our, of course, our associative operation, and it's recognizing, all the different cases that we need to implement. False with anything is false, and then we just provide anything with false is false. And the only case that you need to worry about is obviously if you get two trues, you're dealing with true. Okay. And then we could define an instance monoid Boolean A where empty is true. And this becomes the obvious case here. All right. If you actually recall, if we'll go back to our definition of what a semigroup is and what a monoid is, it'll become immediately apparent that the monoid instance, as defined here, it is not actually taking in the requirement that Boolean must be a semigroup. All right. Meaning Boolean does not need to provide an associative operation in order for it to be a monoid. All right. But the fact that it does this does not mean that there doesn't exist one. It's just that the uh, associative operation is not necessarily unwrapping any sort of values from the underlying type to get the information. All right, because we're not combining any of the underlying type variable values as defined by Boolean here. All right, you can see here. So let's show this now in action. Let's say we have false prime, true prime. We're good. If we do false, true, you can see that we're getting that. If we do false, true, and empty, we get true. If we do true, empty, and true, we get true. We also get, we can also use, like I showed you earlier, append. And all of these now are available at your disposal. You can use disposal, sorry. You can also define, you can also use, append as an infix operator, and you're good. And finally, of course, you can, now that we have Boolean, we can actually go and concatenate a bunch of stuff. And this is going to do what we're expecting it to do. And that is do a reduction or a fold of the underlying list. No, we don't need to worry about that. We talked about identity. The only other thing I'm going to mention about identity, even though I've probably beaten the I'm beating a dead horse, is that just recall that the identity function is returning the same value that you provided once that's attempting to be applied to the identity. There's no concept of identity without operations, okay? You need to know what operation you are dealing with in order to determine the identity of that operation for the given type. So there's two things when you're talking about identity that you need to be aware of. The operation that you're actually applying and the type that upon you're applying it to, because then that's going to determine what it is. Examples, obviously, we saw this before with numeric types. If you're talking about addition, you're talking about 0. If you're talking about multiplication, you're talking about 1. Two different values because two different operations for the same type. All right. So operation and type will determine what the identity value would be. All right. I cannot stress this enough. So we talked about type classes quite a bit today, and this notion of you know what a type, how to leverage it, actually, especially when we're talking about monoids and semigroups. But we haven't really touched base on this topic at all, which is the notion of what a orphan instance is. And in order to talk about that, we need to go back to what type classes are again. They are unique pairings of classes in the instances for a particular type, right? Um, you can have, in the case of um, different types, you want to actually use new type to go and, especially if you have a particular type class that you may have multiple instances for the same underlying type, you may want to actually go and create new types using the new type keyword and then define your type class instances on those new types. So that way the underlying representation stays the same. This is all what we've covered so far. But you might end up sometimes accidentally defining multiple instances for a single type, and then your REPL gets kind of messed up. All right. This is called an orphan instance. Okay. Um, and this is the only way. The way to fix it is essentially, I think, to use a new type. But we've never actually seen an example of an orphan instance in and of itself. So I think it's important for us to actually cover this example that's in the book. And to show this, I think it requires us to first create a new project. Okay. Actually, we'll create two new files, right? Let me close this, and let's call this listy. So this is an example of a of um, of a list that we're defining multiple monads on. This comes from the references is obviously from section um, from page 594, which I think is important in of the Haskell book. Haskell from Principles. And in here we have essentially a new type called listy, which is taking a type A, and it's going to be the same as the underlying value that it has. We're going to just make this deriving from EQ and show. And let's say that we in here define an instance. We define the semigroup for this listy, okay, where our associative operation for one and the other is nothing more than calling on the two lists getting concatenated. Okay. Now, in this case, now let's say that you now have another file that we call listy instances. Oh, sorry, not listy h. My apologies. That is a yes. Now let's go back and say listy instances.hs. And in here, we go in and we define first import data.monoid. Okay, and we are also importing our local module that we just created, listy, and we define in here our another definition for semigroup. And then in here, we go ahead and define it again. We define listy L listy prime equals listy $M L prime. And now we can define our monoid for listy with the identity being the empty list. When we do this and we try to load listy instances, you're going to immediately see that this following error, which is that we have duplicate instance declarations, all right? That is the safe is defined in listy, and the other one is defined in listy instances. Okay. The way you can address this is you need to first ask yourself different questions. Did you define the type but not the type class? Then if you define the type and not the type class, go ahead and put the instances that you're defining all within the type. So that way all the instances are kind of, the type class instances for the given type are kind of in one place. All right, and more importantly, the type cannot be imported without its instances when you actually import the actual type. Okay, so again, this goes back to how modules work in Haskell. When a given type is available, all of its available instances, type class instances, get registered with the type system. So this way you can actually use the operations available for those given type class instances that are there. So any generic algorithms, for example, where one particular operation must be present, if that's automatically imported, you don't have to think twice about, oh, I have to also import the type class instance in order to actually use this operation. All right. The other thing is important is if you define the type class but not the actual type, and you're like creating a new type class, then you have to worry about putting everything in the same module again. So in both cases where you define one versus the other, try to put everything in the same file. But if neither the underlying type and type class are yours, then create a new type that's wrapping the underlying type, and then you can do this workaround. You can actually then define instances on that type, and you'll be good, and you can actually import it correctly. All right. So that's it for today. Next week, we are going to be covering functors and then work our way up. The one thing that I'm going to end you with is this approach to type design and this approach of defining your monoids with strict mathematical properties is going to, as you especially become more and more familiar with it, you're going to start asking about um, uh, the strength of the given algebra that you're defining on. All right. This is important because as you are, developing larger scale systems, this algebra must provide as many operations um, as it can for all the different types of use cases that you go and build with it. And if there are lower level operations that can be composed together to create higher level operations, then the algebra itself will be sound and very strong. All right. Um, One thing that you might think is having a lot of algebras is that are big is useful, kind of like frameworks. All right. Um, it is better to have smaller, more cohesive algebras with a set of operations like and again, when we're talking about algebra, we're talking about algebra like we're talking about type classes in the Haskell sense because as had mentioned earlier, in Haskell, a an algebra is defined has a type class. Okay, it's a set of operations that can be defined on one or more types. Okay, you're not defining the types, you're defining the operations. Okay, so you might be thinking that a big API interface specification is a good idea, but it would be better to have more smaller, more cohesive algebras that can be composed with each other. And this is one of the biggest things that you need to kind of work through. Um, that And the most obvious example is what we just covered today, which is semigroups. Um, and the main reason for this is because a, it allows you to define strict supersets of each other and allows those different kinds of supersets to being available. So common operations being around is allows you to then pick and choose which subset of it is available without having to import everything else. So if you only need an associative operation, you can only deal with semigroups. If you're dealing with the full blown of things, including identity, and you want to have proper catamorphisms, then you're writing a monoid. You need to think about monoids. The point is smaller type classes, smaller algebras, more cohesiveness will allow you to compose and build larger scale systems in a much more cohesive manner than having big APIs because for one thing, you may accidentally duplicate stuff. This is all stuff that I'm reiterating that you probably know from other languages that when you're dealing with interface design. The same rules apply here in most cases actually, when you're defining type classes. And in fact, you should try to make sure that you follow them much more rigidly when you're coming into the Haskell world. Although in other languages you may not be able to. So I'm going to end that with you there. See us next time. I wish you all happy holidays, and I will see you